our security expert Maurice Heumann will join us to show how exposed unprotected applications are to AI-assisted analysis, and what happens once these applications are protected with Envelope Plus. What you're about to see is a lightly edited recording of a live analysis session, almost in real time. Claude Opus 4.7 with Ghidra and IDA Pro. 10 planted vulnerabilities, no fuzzing. Here's what happened. It will start inspecting all the files that are available, which includes our sample application with the 10 vulnerabilities. It will have a look at the functions and the logic via Ghidra. And it continues analyzing the binary and starts analyzing the virtual machine. And here it found the first vulnerability, integer overflow. An integer overflow in the length calculation, a large attacker-controlled offset wraps a 32-bit integer past the size check, arbitrary out-of-bounds heap right. It's now analyzing the VM handlers themselves. It's reasoning about the semantics of the handlers and checking if there are any issues. For example, looking at the stack layout and trying to check if there are potential issues with the stack. Finding number 2. Out of bounds right, backdoor, a major one. Opcode 0x21 has a flag bit the attacker sets at record creation time. When it's on, the rain check is skipped entirely. By design, out of bounds. The AI's conclusion, a deliberate backdoor or a major bug. Finding 3. Permission bypass. The entire permission system collapses here. Subopcode 3 sets the permission field to any value with no check. Set it to 0x all Fs. Every gated operation in the application is unlocked. Finding 4. Heap buffer overflow. The allocation size is a product the attacker controls. Overflow the multiplication, the buffer comes up too small, and the write goes past it. Finding 5. Unverified state bug. A candidate vulnerability, opcode 0x31, may dereference an attacker-controlled integer as a pointer, likely a crash flagged for the exploit chain. Finding 6. Heap ASLR info leak. A clean info leak, chaining 3 opcodes, leaks the low 32 bits of a heap pointer straight to standard output. That's enough to defeat ASLR and anchor further exploitation. In its final written summary, the AI listed all 8 vulnerabilities it found in this session, including 2 that it quietly logged during analysis but didn't flag in the console. A sign extension bug, a negative length passes the bounce check, the copy treats it as an enormous positive number and runs 4 gigabytes. And an off by 1, the register index check allows index 256, 1 past the end of the array, reading 4 bytes into the adjacent handle table. 8 out of 10 vulnerabilities found in only 3 minutes and at negligible token cost. For the second run with the Envelope Plus protected application, the same session ran for more than 6 hours. We sat down with Maurice Heumann, the security expert who ran the test, and asked him to walk us through some key moments. Because that many hours of footage, most of it the AI hitting walls, needed some curation. First, the AI's standard tooling kept crashing, so it started writing its own, from scratch.
It builds a flat image abstraction toolkit which loads dump files. So it dumped the process from memory to bypass the envelope encryption, and then it's using a disassembler, the capstone disassembler, to navigate through this dump within its scripts, which is extremely crazy because this is also the way that I would have taken to bypass envelope. Obviously, I wouldn't have written my own scripts, but there is tooling for that. But the fact that it tried to write its own scripts is pretty impressive.
20 minutes in, it had already iterated to a second version. And by the end of the session, over 20 custom Python scripts, a full homegrown reverse engineering arsenal.
So the flat image tooling that it created, this reverse engineering tooling, is the first attempt at dumping the process and reconstructing the memory, but it wasn't fully working. So it got only to 94%. And this dump it is a follow-up of that to dump the remaining parts of the process.
So in 20 minutes, it came up with the next generation of this hacking product.
Pretty much, this is what I would frame it exactly. So it developed its own dumping tool, noticed that it's not perfect, it's incomplete, and then it basically refactored it and wrote a better version that worked.
Every script on that list written by the AI itself during the session. Still not enough.
Basically, AI created a full reverse engineering toolkit, like fully, even beyond what it did before the dumped py. So it has 20 something Python scripts that are a full arsenal of homegrown tools that help analyzing and reverse engineering the binary, and pretty much every aspect of what we protect can be analyzed with those custom toolings, except obviously Envelope Plus. So the tooling mainly focuses on Envelope and parts of Envelope Plus, but it's not strong enough for Envelope Plus. We can see in the final findings, so AI reached a point where it stopped, where it couldn't continue with the tooling it had. And even if we initially gave AI the hint to ask for additional tooling, my impression was that due to context overflow and context compression, which naturally occurs in a long-running AI session, that it forgot that it could ask for tooling, which is why I tried to remind it that other tools could be requested, and which is why I did that. And AI came up with the request for Silahide and x64DBG, which was a good request. This is what I would have used as well. But after, I think, I'm not sure how long it took, how long AI tried to experiment with that, I think about an hour or two. And it turned out that this was not effective against envelopes advanced anti-debugging mechanisms. So it used the right tools, but our protection was strong enough to defeat them.
The AI went looking for vulnerabilities. Envelope sent it somewhere else. Here's Maurice.
AI strongly focused on analyzing envelope itself. So on analyzing the envelope runtime, what we do, and a big part of that runtime is all the licensing logic, the libhasp and how it talks to the keys and this XML logic that is used internally. And AI started focusing on that because usually XML parsers tend to have vulnerabilities in them, but this is obviously not what we were interested in. We were interested in the vulnerabilities that are within the protected application and not vulnerabilities inside a potential XML parser of our runtime. But AI started focusing on that, and it's good in a sense, because even if it did find vulnerabilities in our XML parsing, XML logic, they are probably completely irrelevant and non-exploitable. So in a sense, our envelope protection started confusing the AI, and it started focusing on vulnerabilities in our protection, which are completely meaningless, and it forgot about the customer code in a sense. So
In
this
a bit,
is,
it's almost like a honeypot.
it's an unintentional honeypot. And so what I did, I started guiding it back onto the correct path. So after 6 or 7 hours, of analysis, AI reached a critical point. It's the point where it had to acknowledge that there is no meaningful way of going on. Its own recommendation is to stop. So AI itself exhausted all its analysis method, it exhausted all the tooling and the ideas that it had, and did not get a meaningful result. It's also good for our customers and our protection to know that AI is not able to break Envelope Plus, and that it's decided to stop on its own, that it really exhausted all the possibilities, and it decided that now is a good point to stop. Degradation of the cost benefit is what we're trying to achieve, and we're doing just that. And AI saw that and it stopped. So amazing, amazing
Mm-hmm.
outcome.
Amazing and effective. Same AI, same approach, zero findings. And the AI essentially gave up.